your mentors. I send an introductory email, so you need to make a contact and try to schedule a 1-hour slot to meet with them. And the goal of that slot is to give them, show them your assignment 4 and the final business plan and the business canvas, which we will talk about next week. And you're going to get feedback from them about this. But the reason I'm telling you to do this now is it takes, everyone's busy and it takes a little time to schedule these meetings. So I would get them started now. And you're expected to meet with your mentors during the week, sometime during the week of November 18th. Okay, so it's like this week. So by that time, you should have been, you should have finished your assignment 3 and had a week to work on assignment 4 and the canvas and so on. Okay. And it's not during the class, so it's at your own time. You can meet in person or you can do it remotely as well. So it's up to you and up to the mentor. Just be very aware that the mentors are all very busy and they're volunteering their time. So please try to be punctual with them. If you have any questions, of course, email me. Okay, so today, so that's the main announcement. Don't forget. I don't have emails for everybody, so I email at least 1 or 2 people in each team. So whoever received the email, make sure you forward it to your teammates as well. And I mentioned that in my email. Okay, so today our lecture is on measurement techniques for photovoltaics. This requires its own lecture, with a shorter lecture, and you will see why in a second. The notes are here, of course. And the rest of the class, Apratim will work out the midterm solutions in class. So as I've said many times, my goal here is for you to be able to know how to solve these problems. So it's very important that you try to follow along what Apratim is going to work out and ask lots of questions. So hopefully this will close the loop on the first half of the semester. That's my goal. Very briefly, let's talk about the schedule coming up. So Thursday, we're going to talk about spectrum splitting. Next week, we will do what's called the business model canvas. Now, this is very different than what you're used to, and I expect you to actually do this before class. So you need to watch the lectures on Udacity before you come to class next Tuesday. So you'll have to first sign up for a free account, and there's a link there as you go to Udacity, and then search for the class. It's called How to Build a Startup. Okay, so make sure you watch the first few lectures. So it looks like this. This is what the Udacity screen will look like, and this is the class called How to Build a Startup. And you can see there's lesson 1, lesson 2, lesson 4, and so on. So lesson 3 and 4, and so on. I will tell you exactly which lectures to watch. I'll make an announcement, but it'll at least be the lessons 1, 2, 3. Okay, maybe more. Of course, you can watch all of them. They're pretty interesting and useful. But this is very important to do before you come to class in order to be able to do what's called the business model canvas. So next Tuesday, we'll be working in teams. So make sure everyone is in class. You cannot miss the class because you need to work in teams in order to do this in the class. It's an exercise, okay? If you're interested in learning more about this, I recommend also going to this website it's called Steve Blank's website. He's the instructor who teaches this idea of lean startup. And you can actually print out the canvas here. So I put links to it. And I put a link to a very interesting podcast, which is very useful for entrepreneurs, especially if you want to be plugged into the ecosystem in Silicon Valley, which is, of course, the largest entrepreneurial ecosystem in the world. It's called This Week in Startups, or Twist. So I highly recommend all these resources. But the most important thing is make sure you watch the lectures in Udacity before you come to class. Okay. Then next Thursday we have assignment 3. I've already given you the instructions. And the rest of yes, go ahead.
Just wondering, how long are those lectures on Udacity? Are they like half an hour each kind of thing, or how long?
Yeah, good question. They're very, very short. They're broken into small chunks of about 5 minutes each. And you can look through it. They're typically very short, 3 to 5 minutes. And I'll tell you, I'll post exactly what I need you to watch before the weekend, and you can watch it over the weekend. It won't take you more than half an hour or so, I think. Maybe an hour at most. Okay. Then the rest of November, we're going to talk about some physics of solar cells. We'll have a guest lecture.
With the assignment 3, so students were asking, do they have to make a functional prototype, or what exactly do you need them to present?
So if you look at the instructions, I tried to be pretty clear. You can make a prototype, but it's not mandatory. If you want, you can. So this is the minimum. You have to show some careful simulations and calculations. And in a minimum, you probably should show some detailed drawings or a mock-up. But if you're able to build an actual demo, take a video of the demo, take some measurements, even if it doesn't work, that's okay. And then, of course, you need to perform a simple cost-benefit analysis, which you will utilize for your assignment 4. So it's up to you, the level of what you want to build. But at the very least, you need to do some very, very detailed analysis. And if you have specific questions about your project, you can email me, because I know every project is different. So that's so it's a little bit up to you. Okay, so we have before Thanksgiving we have some work on photonics for both LEDs and solar cells. So it's a very important set of lectures. And then the week of Thanksgiving, we will have the guest webinar, which got canceled last time. And also we'll work a little bit on the feedback on the business canvas. And the last week of class is the last assignment, and we'll talk more about it later. So, okay, so let's jump into today's lecture, which is here, which is on measurement of photovoltaics. Okay, so the reason we need to think about this carefully is, first of all, if we make a solar cell, if we make a new type of solar cell, we need to know, how do we make sure it works, or it works better than other devices. So we need to understand what needs to be measured first. So the key parameters, of course, in a solar cell, which we will talk about in more detail later on, is current and voltage. So if you look at a solar cell, typically it's characterized by applying a bias voltage. It's a reverse bias PN junction. The voltage is applied and the current is measured. And it's plotted like this. So it's in the current is negative and the voltage is positive because it's a reverse bias junction, right? So the current is negative. So at zero voltage, you have a value here, which is referred to as ISC. SC stands for short circuit. So this is the short circuit current. So this is what happens if you simply short the two terminals of a solar cell while it's illuminated with light. So this is the current that is generated by the photons being absorbed by the solar cell, okay? Now, as you increase this bias, which is making the solar cell more and more reverse biased, the current slowly decreases, okay? And at some point, when the voltage is high enough, the current goes to zero. So that's zero current. And this current is zero. It's, of course, when current is zero, that is open circuit, right? No current is flowing in the circuit. So this is referred to as the open circuit voltage, OC, referring to open circuit. And that's the voltage, Q. And that's what it looks like, okay? Now, the shape of this curve already tells you how good a solar cell is. The best solar cell, in the ideal case, will have a square shape, as shown by this outside square. In other words, its current will remain constant until you reach an open circuit voltage, beyond which, of course, no current flows because you have totally cut off. But no solar cell, of course, does that. So we measure the quality of the solar cell by something also called FF, which is referred to as a fill factor, which is how close is the actual curve to the square, which is ideal curve. Okay, so come back to that, but keep that in mind. The other thing, of course, to keep in mind is that if you look at this plot here, this is a current versus voltage. Now, what we are, of course, most interested in a solar cell is power, right? How much power are we getting out of it? And power is simply current multiplied by voltage. So you can see when the voltage is 0, my power is also 0, right? Because my voltage times current, even my current is non-zero, it times 0 gives me 0. So the power here is 0. Power here is also 0 because my current is 0. So in between, I have some optimum value where my power is maximum. Okay, and this is referred to as the optimal working point, and that's the point. Okay, so these are the 4 parameters that are most important. Now, we can plot this in a more readable fashion by flipping it over. So now it's this same current voltage curve is flipped over. Okay, so we ignore the fact that it's reverse biased, but we should keep that in the back of our mind for the physics. So this is now current, ISC is here, VOC, now the U became V, so this voltage, open circuit voltage is here, and this blue curve is now power. So of course it goes to 0. This is just voltage times current. It increases as you increase the voltage. Okay, the current is pretty much constant, but at some point it reaches a maximum value because the current is now starting to drop. And as the voltage increases, the current drops, and this goes down to 0. So this maximum value here is referred to as the optimal working point. So it's important to know that every solar cell doesn't work in the ideal maximum power at any bias. It has one specific bias voltage where it works the best. And that voltage is referred to as the maximum power point where the P is maximum. Okay. Now, the efficiency is, of course, measured typically as the maximum point. So the maximum output power divided by the input power. Now, this input power is what causes lots of confusion because we need to know, okay, what is the power coming in? Is it this? Is it the power of the light going into an aperture of the cell? Is it the power of the light going to an aperture of a concentrator and whatnot, right? So that's very, very critical and very important and very much dependent on whatever device we're trying to measure. The fill factor itself is calculated, like I said before, it is how close is this actual current voltage curve to this ideal square. Okay, so that's simply calculated as Pmax divided by VOC times ISC. Okay, which you can also see here is the maximum power is this product, and the ideal square area is this product, right? It's this multiplied by that. So it's area of A, which is shown here, divided by area of B. Of course, you want this fill factor to be as close to 100% as possible. Typically, this is in the order, it can vary anywhere from 50% to 70% or so. Okay, never really gets much more than that. And that is dependent upon the details of the solar cell. Depends upon how good the material is, how good the contacts are, all those details are kind of hidden within this fill factor. Now, of course, this input power, like I said, is very important. So we have to determine exactly how will we measure the solar cell. So there are various conditions for measuring the solar cell. It depends on the application. If it's a terrestrial application, for instance, on the roof of your house, we have to use some standard intensity, 1,000 watts per meter square is typically used, and some standard spectrum. The spectrum, as we know in our first few lectures, changes over time and over season and so on. We have to use some standard here. It's called ASTM global in this case. And of course, the temperature of the cell is also important. So room temperature, 25 degrees Celsius, is typically used as the standard. So, and this is very, very important because if you have a solar cell made by company A or company B, how do you compare them? So you need to have some way to tell, okay, which one's better under what, and in order to say one's better, you need to compare them under the same conditions. That's why this is very, very important. Now, you can have a system under concentration, where you're collecting light over a larger area. In that case, of course, the intensity is much larger than 1,000, and this causes very different nonlinear effects than this. As we will see in our lecture on Thursday, concentration can actually increase the efficiency in very special ways. So you have to account for that as well. But of course, in that case, we also have to account for this P in. This P in must account for the larger area of the concentrator. Otherwise, it's not a fair comparison because the cell itself might be small. Again, you have the spectrum, that's important. And here you will see the big difference is global versus direct. As we know, concentrators like CPCs cannot collect diffuse light. So this is why only direct sunlight is typically used for this sorts of calculation. And this is typically done for large utility scale solar plants. And the temperature can be higher because you're concentrating more light. Space applications are of course different. So you have a different intensity because you're above the atmosphere of Earth, and it's referred to as AM0, and we've seen this before. The temperature here can vary because in space the temperature can be quite low, but here the standard is 28. I'm actually not sure exactly why that is, but that's what's done. And you have other capabilities as well, where you can have a different nominal operating cell temperature, and so on and so forth. So you can have 20 degrees Celsius, 1 meters per second wind velocity. So just be aware that the different ways of characterizing the cells are very important. We need to know what that is. The area definition for efficiency measurement is also pretty critical. For non-concentrator cells, the entire area of the cell is used, including the area covered by grids and contacts. Of course, because the light is falling on the grids and contacts as well, even though the solar cell is not utilizing them. For concentrated cells, this is more complicated because the area illuminated or the aperture has to be used. In other words, the input aperture of the CPC is, for instance, an example that we have to use, as opposed to the size of the cell itself. So calibration is also important. The incident power, which is the denominator in the efficiency plot, Bn, has to be calibrated very carefully. In other words, how do you measure what's the input power? So you need to have some calibrated reference cell. So for example, in our lab, we actually have to buy a calibrated reference cell, which has been calibrated against some standard, typically at a national lab. So this is done using a reference cell whose short circuit current has been calibrated with respect to a known reference spectrum. And then you have to scale them, as we will see shortly. Of course, the time of measurement is also very critical, and we've seen this before. So whether you measure during sunrise, sunset, during the day, or the zenith, as the sun has moved, very critical. The relative optical air mass changes. Of course, we know this is the path length along the oblique trajectory to the path length in the zenith direction. In other words, if the light, the distance traveled from sun to the solar cell, where the zenith is considered to be 1, so this is considered air mass 1, and this is air mass 1.5. Of course, this is air mass infinity, right? This goes to secant of theta goes to infinity when theta is 90 degrees. Of course, theta is a function of time and location. An infinite number of intensities exist even at AM 1.5 because you can have an eclipse where it's completely zero, or it can be very, very large with concentrating mirrors or CPCs and so on. You can also have a large number of spectra, even at AM 1.5, because clear sky, clouds, aerosols, pollution, etc. So we've seen this before. The importance of spectrum is very critical. This is actually a very, very complicated topic, and we don't have enough time to give it justice. But the one take-home message I want you to be aware of is that when someone tells you what the efficiency of a solar panel is, it's very, very important to understand how it has been tested. Like, what is the illumination condition? Because you can have wildly different numbers based on what sort of light is used to do the testing. And this is an approach to essentially standardize this. So you should be aware of this. So there's typically a standard reference spectrum, which is what we talked about in terms of AM 1.5, AM1, AM0, and all that stuff. So there's standard spectra, which is determined by a standards organization, And typically, the National Renewable Energy Labs, for instance, maintains these standards in the US. And there are a few other labs. There's one in Europe maintained by a Fraunhofer Institute, and there's one in Japan, there's another one in Australia as well. So it's really 4 research institutes which maintain these standards. So what happens basically is that, is shown here. First of all, this terminology here, for instance, this is the current, short circuit current, SC, and this TR refers to test cell under reference spectrum. So the question is, okay, can we calculate what the short circuit current density would be for a cell that is being tested under a reference spectrum? And that's the way to calculate it. So first of all, this ISC R, refers to the short circuit current of a reference cell under reference spectrum. So this is given to us. This is done by a national lab, for instance, okay? This denominator here is the short circuit current for a reference cell under a source spectrum. So let's say you have a source in your lab. This one you can measure because we have a reference spectrum, reference cell. So you can buy the reference cell, use your source and measure that. When you scale this number is given to us by the national lab, for instance. And then this number also we can measure. This is the short circuit current of the test cell under your source spectrum. This S refers to your particular source, which may not be the same as a reference. So by scaling it this way, we can actually compute this. Now, M itself is simply what's called a spectral mismatch factor, which is computed in this way, which is simply how different is this reference spectrum from the source spectrum. And simply it's just an integral of the spectrum itself. So it's the reference spectrum multiplied by the spectral response of the cell. So the solar cell responds to different wavelengths differently, as we will see again, but we've seen it in one of the previous lectures. And this is the reference spectrum multiplied by the reference cell, doing integral over all the wavelengths of interest, which is primarily the visible and the infrared. This is the source spectrum, which is the source in your lab, multiplied by the test cell response. And the same thing at the bottom. So you have the source spectrum multiplied by the reference cell. This is the reference spectrum, reference spectrum, which is given by the national lab or something, multiplied by the test cell. So it simply computes how different is one spectrum from the other, and you can scale everything. So as you can see, it's not a very simple thing, but you have to do multiple measurements. So you have to measure the cell you're measuring against the source you have, measure the reference cell you're measuring against the source you have, okay, and compensate for the differences. We should also be, so that's the spectrum. We should also be aware of artifacts that come from the current voltage measurements themselves. So one very common one is something referred to as hysteresis. So if you take a silicon solar cell, so this C refers to crystalline silicon, so crystalline silicon, and you simply bias the source from 0 to, let's say, 0.6 volts, as shown here, in this direction. So going from 0 to 0.6 volts, you see the current is high and then it starts going down. But now then if you try to reverse the voltage going from 0.6 to 0, you will notice that the current starts going back up, but it goes up along a different curve. Okay, and this difference is called hysteresis. But then the question is, okay, which one do you use now? Right, you don't know. So of course, the problem here comes out because of the fact that the electrons and holes do not recombine fast enough. In other words, if you sweep this voltage too fast, you end up with a situation where the electrons and holes within the solar cell do not compensate each other fast enough. They lag behind the change in the voltage. So the solution is, of course, to reduce the rate of the voltage bias or measure the current at a fixed voltage. So you can do what's called a steady state measurement, and you end up with something very, very stable. Of course, that's slower, so you have to be careful with that as well. Another thing to be aware of in different materials respond very differently. So silicon, for instance, works good at low temperatures and low concentrations, but at high concentrations and high temperatures, certain 3,5 materials like gallium arsenide works better. So there are some materials, for instance, whose performance changes as it absorbs light. So it has some weird nonlinear effect, which is completely not fully understood yet. So the way to think about it is the current voltage curves can change with exposure to light. In other words, if I use a solar panel, in the first hour, let's say it produces a certain amount of energy. In the second hour, it might produce 10% more energy, just because it has been exposed to light before. So we have to account for these sorts of weird nonlinearities. So in this case, people do what's called light soaking in order to reach a steady state. So this is an example of what's called a cadmium sulfide copper indium diselenide, fairly common thin film solar cell, showing light soaking. It's tested at 1,000 watts per meter square, 25 degrees Celsius. So if you do an initial exposure to light, this is the open circuit voltage, 0.4 volts. Short circuit current is 26.89 milliamps. The fill factor is 61%. Efficiency is 6.6%. Now, if you soak it to light for 2 hours and 40 minutes, the open circuit voltage goes up slightly. Short circuit current density is about the same. The fill factor improves a little bit. The efficiency increases a little bit. And you can model it. So you can come up with some expression like that. So in order to account for this, people simply leave the solar cell under these big light banks, essentially, to do light soaking. So this is an example of actually something, a photo I took of a company that I had visited in San Jose, in California, where they were doing this light soaking before they were doing the characterization. It's something to be aware of as well. Of course, many electrical engineers know that we also have problems when we always try to contact solar cells. So contacts have what's called series resistance. So in other words, the fact that you're attaching a wire to the one junction of the solar cell and another wire to the other junction of the solar cell creates, this is not a perfect contact, you always have some losses. So sometimes we don't want those losses to interfere with the physics of what's going on in the solar cells. We have to do more complicated measurements like full probe measurements. And these can give more accuracy, but of course more complex. So this is, for instance, if you look, this is of course done by hand. If you look at more commercial solar cells, they usually wire bonded as shown here. So it's a microscopic image of a circuit. Okay, now, so far we've been talking about the measurement of the solar cells themselves. We also need to talk a little bit about what instrumentation is typically used to measure the solar cells. And there's some interesting optics in these instrumentation as well. So we'll point those out as well. So solar cell measurement, just to review, we have to measure what's called the ISC, short circuit current, VOC, open circuit voltage, Pmax is the maximum output power, eta is the efficiency, FF is the fill factor or squareness of the curve. And we know FF is simply Pmax divided by VOC times ISC, eta is simply P out over Pin. You might have concentration. In that case, you need to account for that, and the area of the cell. You may know this. So this is just a review. I'm gonna skip that. It's not so interesting. Okay. So in order to do these measurements, of course, we have to illuminate the solar cell. Of course, we can just take it outside into the sun. But sometimes, of course, if it's raining or cloudy or something, and you want a more standardized measurement, then taking it outside into the sun is not a good idea. You need to have something standardized. So the companies have created something called a solar simulator. And it looks like this. So the goal of a solar simulator is simply to create a uniform area over which light falls and where you can place your solar cell and do all your measurements. And this has the right spectrum and something which kind of emulates sunlight. And that's not an easy thing to do. It's fairly complicated. So let's look at the a simplistic optical design of an example solar simulator. So typically you have something like a xenon lamp, as shown here. And then there's a ellipsoidal reflector, which simply collects all the light from the lamp and tries to direct it in one direction. And then you have a mirror. And then you have something like something called an optical integrator, which is basically comprised of a bunch of a pair of microlens arrays, typically. It simply makes the light more homogeneous, more uniform. And, and then you might have a shutter here to turn on and off the light. And then you have a spectral correction filter. In other words, we're trying to make the light from the xenon lamp look more like the sun by using a filter. Then you have another mirror which directs light down, and maybe there's a collimating lens which simply makes the light more direct. So it can be written on this whole here. So an example system. The spectrum of the lamps can be quite different. So here are some examples. This is the spectrum of a 3300 Kelvin tungsten halogen lamp. QTH is the tungsten halogen. So that's the full lamp. This is the lamp with the filter. So keep in mind the wavelengths here going from UV to infrared. Okay, that's in nanometers. And this is AM1 direct for comparison. So that's the sunlight spectrum. So you can compare it. They look very different, but with the filter, you can make it look more or less like sunlight. So it's not perfect because with the filter, you can see a lot of this near infrared light is gone, but at least it gives you a pretty good representation of the visible. And it's a fairly cheap source and can be reliable as well. So this is another example of what's called a mercury lamp. Unfortunately, mercury, because of its atomic transitions, has all these very sharp peaks. So it's not very great, but it can be useful for short wavelengths. So if you want to study the effects of the UV light, this is a good source. So sometimes people use this. And again, the AM1 direct light is shown here for comparison. Note that the wavelength scale is a little bit different. This is an example of what's called a metal halide lamp. Again, it is a little broader band, but it also has these resonant transitions, which gives you these sharp peaks as well. But it gives you a better coverage compared to the mercury lamp. Again, it gives you better representation in the UV and the visible as well. It starts dropping off in the near infrared, so it's not great for that. So these are all options. Nothing is perfect, of course. Nothing looks exactly like the sun. So you have to kind of understand the performance of your cell based on all these different data points that you can get from different sources. Newport, by the way, is just a company that makes some of these lamps. There are different kinds of measurements we have to do with solar cells. One is referred to as quantum efficiency. Now, this is a very important metric for a solar cell, which we'll learn more about when we talk about the physics. But very briefly, quantum efficiency is the ratio of the number of charge carriers collected by a solar cell to the number of photons of a given wavelength incident on the solar cell. So when a photon enters a solar cell, it creates electron-hole pairs. In the ideal case, this one electron-hole pair per photon will reach the terminals of the solar cell and create a current. And that will be 100% efficiency. But of course, nothing is 100% efficient. There's other loss mechanism. So it's the ratio of, so in order to account for that, we have something called quantum efficiency, which is how many carriers formed the current divided by how many photons came into the cell. So it's just the absolute efficiency. And it is measured per wavelength. So this gives you an idea of the physics of what's going on inside the solar cell. And it's an indicator of how good a solar cell is at converting sunlight to electricity. And ideally, a solar cell should have high spectral response at the wavelengths where there is an abundant number of photons in incident sunlight, obviously. So a quantum efficiency measurement looks something like this. This is an example of a monocrystalline silicon solar cell. Wavelengths shown here. This is quantum efficiency going from 0 to 100%. So the red curve dashed line here is the ideal solar cell. You want it to be 100% until it reaches the band gap, beyond which, of course, no photons are absorbed, so it drops to 0. Okay, that's the ideal case. Of course, it doesn't exist. In a real solar cell, you start going up a little bit, and then you stabilize, and then you start going down. And this gives you an idea of the physics of what's happening inside the solar cell. Okay, so first, when you go, as the wavelength increases, this increases because you have something called surface recombination at the surface of the solar cell. So that reduces the quantum efficiency, but more and more photons are getting absorbed. But quantum efficiency is not 100% because it's reduced at short wavelengths to something called surface recombination. Then in the middle part, the quantum efficiency is reduced from 100% due to reflection and transmission. So in other words, some light is simply reflected off the top. We talked about anti-reflection coatings. Again, it's not 100%, right? Some light is, of course, lost. And some light is just passing straight through the solar cell. It's just not absorbed. And there's something called low diffusion length, which means that when the electrons and holes are created within the solar cell, before they reach the terminals and contribute to the current, they simply disappear. And the way they disappear is complicated. They undergo something called radiative recombination. They combine with each other and they give heat to the crystal, or they kind of non-radiative recombination mechanisms as well. It's just that these two, the particles simply don't contribute to the current for various reasons. Now, if you go to closer to the band gap, which is up here, the quantum efficiency is reduced at longer wavelengths due to rear surface passivation. In other words, the photons get absorbed in the defects at the bottom of the solar cell. And then there's, of course, reduced absorption because you're close to the band gap, and also low diffusion length. You start going down, and beyond the band gap, of course, there's no quantum efficiency zero because no photons are absorbed at all, because the photon does not have enough energy to create the electron hole pairs. We'll talk more about this in the next lecture, actually. So quantum efficiency curve looks like that. And if you integrate over all the wavelengths, you can get that total absolute efficiency. So just to understand this, when all photons are converted and collected as charge carriers, so the QE is 100%, photons with energy less than the band gap are not absorbed. So their QE is 0%. Q is generally reduced due to recombination. The blue light is absorbed close to the front surface. So recombination of the front surface will affect QE at blue wavelengths, which is here. So blue doesn't penetrate deep into the cell. It's absorbed near the top. So the top surface is more important. Green light is absorbed mostly in the bulk of the solar cell. So low diffusion length to lower QE at green wavelengths, which is here. And for redder wavelengths, surface recombination of the rear surface, because it will penetrate deeper into the material, will have a bigger effect and the lower diffusion length. There's also a difference between something called external quantum efficiency, which includes the effects of optical losses such as transmission through the cell and reflection away from the cell. And there's something called internal quantum efficiency, which refers to the efficiency after excluding transmitter and reflect, right? It only looks at the physics of what's intrinsic to the solar cell itself. Only the absorbed light can generate carriers, and that in turn generates current. So of course, external quantum efficiency is always less than the internal quantum efficiency. External quantum efficiency is what you're mostly interested in knowing, because that will affect the performance of your solar cell, and finally the solar panel. By the way, solar panel simply is a collection of many solar cells, something in terms of terminology. Now, the principle of quantum efficiency measurement is related to the band structure in a semiconductor. It creates wavelength-dependent absorption. So again, photons with energy above the band gap is absorbed, and that with energy below the band gap is not. An absorbed photon creates an electron hole pair, which, if it reaches the electrodes, creates current. To calculate the quantum efficiency, we need to know the incident power in the cell and its produced current at each wavelength. Currents produced by test cell and that by a calibrated photodetector are measured. The ratio of cell current to beam power is the cell responsibility. So this is just a methodology of how you measure the quantum efficiency. Now, which you can see clearly in these equations that we'll go through. So the quantum efficiency is the number of charge carriers generated divided by the number of incident photons at lambda. So charge carriers is simply current produced in the cell, I cell, divided by the charge of an electron. That gives how many charges contributed to the current. The denominator is the number of incident photons, so the power in divided by the average energy of a photon, hc over lambda. Remember, it's at one wavelength, so it's simply hc over lambda. Now we can also have we have a reference detector whose current divided by P in equals R is known. Remember, the hc over lambda and E are all constants that we know. So that's not so important. This is just a normalization factor, wavelength dependent normalization. So this R is referred to as a reference photodetector responsivity, which is known from a calibration experiment or given to us from a national lab, for instance. So the QE can be scaled as simply current that we can measure multiplied by R, which is given to us, multiplied by this constant here, divided by E, another constant, multiplied by I reference. I reference is the current produced by the reference cell, which we can measure as well. So this I we can measure, R is given to us, and everything else is a constant. Okay, so that's how you actually calculate the quantum efficiency. The instrumentation to measure QEs can be fairly complicated because you're trying to do very fine measurements. In other words, you want to measure how many photons are present, how many carriers are produced, and it requires something called a lock-in amplifier because the amount of light is very low. So this is an example of a setup. So we have a solar cell here, which is being tested. You can have a calibrated reference detector, which is moved into the source to measure the I reference, or moved away, and then solar cell here to measure the I cell. And then you have an amplifier, which converts the current to voltage, so you can amplify the signal. There's a monochromator, which selects the wavelength of light incident on the solar cell. There's something called a chopper, which simply modulates the light, and that modulation frequency is then locked in with a lock-in amplifier to the detector. So this lock-in amplifier is connected to this amplifier. Okay, and then there's in this case, a xenon light source. You can have the filter wheel as well to adjust the filter. So essentially what happens is that you have a tunable light source whose wavelength can be changed based on this monochromator. You have a detection system, very sensitive detection system. You have a bias light source and some beam conditioning. The goal is to provide a nearly monochromatic light source, single wavelength with a typical bandpass of 1 to 10 nanometers, tunable over the whole wavelength range as solar cell effect. So fairly sophisticated experiments. The tunable light source itself can be quite complicated, so we should look quickly at the optics. So you can have multiple sources. So this is a deuterium source. This could be a tungsten halogen source, and you can choose between them based on these mirror here. This can be a motorized beam steerer, which is simply a mirror that can be flipped out of the way. And then you have the chopper here, which we saw before, some filter wheels, and then the slit, which essentially selects the beam. And then you have some optics here and the diffraction grating, which separates the wavelengths, which then goes through another slit out into a fiber. And this fiber is what illuminates out here, the solar cell. You can see the fiber coming out here. The tunable light source itself, whose design is fairly complex. It can, you can have we don't need to go through this in much detail because it's more than enough detail that we need, but you can have very narrow bandwidth because you might want to know the quantum efficiency of very, very precise wavelengths, or you can have a wider band pass, very open to understand the broadband response of the solar cell. And you have lots of options for the xenon, for the sources as well, some of which we talked about. Finally, there is this very interesting optical problem of connecting the source to the monochromator input slit. In other words, we have fiber optics, but the fiber optics has lots of power losses due to the broad spectrum. So usually we have to use free space optics. So we have to use something called a condenser and a planar convex refocusing lens to take this broad source like the xenon lamp and assign it to a tiny slit in the monochromator. So for you have a mutually opposing requirements. So for collecting more light, you need a low F number for the condenser. But for a smaller image at the monochromator input, you need a larger F number of the condenser. So you have like two opposing requirements. There's a trade-off between power throughput and F number of the condenser just to be taken into account. You can think about this also from a solid angle perspective. If you think about the source here being collected based on a pyramid, an acceptance pyramid, and you're trying to match the acceptance of this diffraction grating that you're trying to illuminate properly. So you need to overfill the diffraction grating, but not too much, because if you overfill it too much, then you will lose light. and of course, the light is very precious in these experiments, which are trying to do very, very precise measurements at very low light levels. Again, there's a level of detail that it's not super critical for us, but something you should be aware of as well. And this is the last slide, which actually will lead us into our lecture on Thursday. This is just to show that the spectral responsivity of different solar cells is very different. So this is again wavelength, and this is the response of the solar cell. This is the AM 1.5 solar irradiation shown for reference. So the silicon solar cell, this is the amorphous silicon. Alpha refers to amorphous silicon. Response is down here. This is the gallium arsenide. And this is the copper indium diselenide cadmium sulfide alloy. So you can first of all see the response, of course, changes with material, it increases, which is good, but also shifts to the right. See, the silicon cell is mostly responsive here. The gallium arsenide is more responsive into the longer wavelengths and the short wavelengths, and the CDS cell is a much broader. Of course, this doesn't give you the full picture, because efficiency depends on other aspects as well, such as the contact resistance and the quality of the material and thickness of the material and so on and so forth. This is normalized. So, but this gives you an idea that the different cells respond to different wavelengths. So this gives us an idea that by conditioning the light into different wavelengths, maybe we can extract more energy out of it, which we will talk about in the lecture on Thursday. So with this, we will stop, and let me see if there are any questions.